this is, we're talking about chaos and Hamiltonian systems, and I'm showing you some of the very end from last time, where we had been talking about periodic orbits, especially in a time periodic 1 degree of freedom system. These are sometimes called 1.5 degree of freedom, the half degree of freedom coming from the time dependence, the periodic time dependence. And that is the minimum that you need to have chaos. So you either need a time dependent 1 degree of freedom system or a 2 degree of freedom time independent system. That's the minimum for chaos. There's a theorem that says you need a 3-dimensional ordinary differential equation to get chaos. So you won't see it in a 2-dimensional, but you could see it in 3 dimensions. There's no guarantee, right? If you have a system that has an action angle representation, so it's completely integrable, even if it's in high dimensions, it will not show chaos. But you could, if it's non-integrable, and we'll look at a case that is not, then you can have chaos. And often chaos is due to, you could think of it as a governing structure are the saddle type unstable periodic orbits and trajectories related to them. So these are the stable and unstable manifolds. So a good example that has been used by several authors, including Wiggins, is the Duffing system. That's the one with 2 wells with an unstable middle point. So we've got the set of ODEs here, and we've put it into extended phase space. So instead of time, we've got theta. So by extended phase space, we mean X, Y, and theta. When there's no time dependence, so when we set the forcing term is here in red. It's epsilon cosine theta. So epsilon is the amplitude of the forcing. Think of the marble in the cart. And so this is the amplitude related to how much we're moving the cart back and forth. Cosine theta would be cosine omega t. So that's the time dependent sinusoidal part. When epsilon is 0, we've got no forcing. When delta is 0, we've got no damping. And that's the situation we'll look at first. In that case, the phase space, at least half the phase space, and we'll just look at kind of the right half well. Looks like this picture down below. And there is a fixed point, an equilibrium point of the system, which is this point P0. And P0 has both unstable and stable manifolds, but they're actually the same thing. We can define something that we call this gamma P sub 0. This is the homoclinic manifold. It's made up of all those points that are on both the stable and unstable manifold, which in this case is this entire, there's this trajectory. Points that start on that trajectory because they're on the stable manifold of that fixed point. As time goes to infinity, they end up at that fixed point. They're on the unstable manifold, so as time goes to negative infinity, they also end up at that fixed point. So going forward and backward in time, they asymptotically approach that fixed point. And well, I'm calling this the homoclinic manifold. It makes, I'm going to draw a picture next where I look at this in time. So I'll add the 3rd dimension. The 3rd dimension being this theta, it's like the phase of the forcing. And then when we, actually just we'll focus on this one. When we'll eventually add damping, but when we add forcing, so let epsilon not equal to 0, then this homoclinic manifold, instead of being a surface, will end up breaking. What do I mean by it's a surface? If I now look at X and Y, and then I have a 3rd dimension, theta, we could draw that picture, and I will find the picture. Duffing. Yep, here. We have a picture that looks like this. So this is This is showing that same manifold, but now we're viewing it as the manifold of, let me draw in P0. P0, that equilibrium point, is just the same point as we go up in time, right? We're drawing things upward in time. I know in past lectures, I kind of drew time sideways. Now I'm drawing it vertically. So P0 as a function of time is just P0. And here we're calling this, it's a periodic orbit, gamma. And what are we sketching on the right-hand side here? These are parts of this is a piece of the unstable, but it's also the stable manifold. As something goes through time. So if I pick a point, let's say this point down here, let me call that Q. Then Q, what is Q doing? Q is moving, it's moving along the unstable direction, but it's also moving through time. So then we end up here. And this is going from phase 0 to phase 2 pi, which is the Poincaré map. So the Poincaré map, stroboscopic map, looks at points and maps them from the Poincaré section. So a time slice or a theta slice, theta equals 0 to theta equals 0, which is also the same as 2 pi. So this point up here, we can call it PQ. So Q gets mapped to the point PQ. And then, well, PQ is down here. And it also marches along. So now here's P2Q. It'd be like 2 iterations of this Poincaré map, and so on. Here's P3Q. And then this would be P4Q, and we've turned this corner, P5Q, and so on. So you can see as we're going forward in time, this thing is approaching the periodic orbit. So this thing is it's an unstable periodic orbit. And what we're showing, this sheet, is the homoclinic manifold of the periodic orbit. All right. This is with no forcing turned on. When forcing is turned on, this surface will split. So let's turn on forcing. That means epsilon is not 0. If you want epsilon's, it's small, but greater than 0. And we get another picture, this one. Let me try to draw it right under the other one so you can see the parallel. So this is the same kind of the same, but in place of, let's say epsilon's small. So instead of a point P0, maybe P0 is here, the points shifted a little bit. Now we've got P epsilon, but there's still a periodic orbit. Maybe we'll call that gamma sub epsilon T. So gamma epsilon T is it's the periodic orbit, still unstable when damping, when forcing is present. And now the stable and unstable have kind of split up. So here I'll draw, this is part of the unstable manifold. And then we've got the stable manifold. And if we were to follow, well, we see that they don't coincide anymore. So the stable manifold of gamma epsilon does not equal the unstable manifold. So this, we call this the separatrix split. And that's going to have consequences. Before the separatrix split, if I sneak up back here, everything that started in this yellow region will stay in this yellow region. So everything, if you want to think of it in terms of, this is a potential energy well, everything starting in this potential well stays for all time. In fact, it's just going to be circulating around the bottom of the well. When the separatrix splits, we're not necessarily going to have that behavior anymore. Things can actually escape from the well. And how does that work? Well, we still have these, we've got these points along which the stable and unstable manifold intersect. So like this point down here in blue. And if we follow it as it goes upward, right, it goes to here. So here, this point Q goes to here. PQ, and then where does that start from? It starts down here, and this is PQ. It kind of rounds this corner, goes here, here's P2Q. So we've got these points of intersection that are on the, if you have a point, if Q is on the intersection of the unstable and stable manifold, then if we look at what happens to PQ goes to, it's going to converge onto the unstable periodic orbit in both forward and backward time. Maybe I'll probably write it that way, as n goes to plus or minus infinity. So instead of having this whole collection of this entire sheet, we've got these set of points, and these are called homoclinic points. And if we look at the details of what's happening in these regions between the intersection, we can get some insight into the global dynamics. So there's a nice sketch in one of the references that I'll provide, but I'll just show it here because it's so cool. All right, here is, this kind of gives an idea. Ooh, sorry there. So this is showing out both the right side well and the left side well, but we're still focusing on the right side well. And so we've got let's start down here at the bottom. We've got the unstable and then the stable directions, and they intersect in certain points. But if we look at, here's this orange segment down here. This is a part of the unstable manifold. And then this green segment is part of the stable manifold. We'll follow it upward through time. What does it do? Well, this green part goes to here, right? That's kind of the outside. The orange part goes to here. And if we were to look at a, just take a section, here's the Poincaré section, and what does that look like? Just flattening it out. Trying to sketch it. A little bit tough to do. Oh man, okay, there we go. All right, so this is this green part, and then the, the orange, and I'll color this side in here yellow. So this yellow piece, should be this yellow thing in here, it's a piece of the phase space that twists around, and then it goes to being here. So we might call this a region. Actually, it's called a lobe. So I'll write it as L. L is a lobe. And you can read more about the whole subject called lobe dynamics if you want, dynamics. But it's about how these lobes move around when you have intersections of stable and unstable manifold. So this lobe L, right, this section up here, if we were to take a slice, this is also our Poincaré section. And what we see from this is that the lobe L maps to being over here. So I'll call this P of L. It's the iterate under the Poincaré section of this region called L, bounded by pieces of the stable and unstable manifold. And this will continue. So if I were to follow this for a couple of more intersections, well, now this is P2 of L, another intersection, we get P3 of L, and so on. And it keeps getting this region to maintain the same area. Because before I turn on damping, this is a Hamiltonian system that preserves area. So the region bounded that's in this lobe, the area of this lobe, and all of its future iterates must have the same area. But there's only so much area inside this region. This kind of region that's kind of inside the well. So that means after a while, these skinny yellow things will become very rectangular, very elongated, and eventually leave the region. But how do we interpret this part right here? So let me do a kind of a backward iterate of L, maybe a couple backward iterates. So here's, this is P inverse L, P -2, so two pre-images of L. This is definitely, this thing right here is definitely a region that's outside of the well. It's outside of the right well. But over time, in fact, over just a few periods of the forcing, all the initial conditions in here, right, they keep mapping from one lobe to the other until they're inside the well. So you could have things that start from outside the well go inside and vice versa. So there's actually a, this lobe right here is inside the well and it'll be mapping outside. Maybe we would call that like L prime, and then here's P of L prime, and so on. That's getting further and further outside the well. So these things are called, because it resembles a turnstile, like a turnstile that goes into a building, they're called turnstile lobes. One is going into a region, one is going out of a region. And I think I have a video of that. Yeah, maybe here. This is showing this is where over here on the left, we've got a fixed point, and then we're showing the boundary given by the stable and unstable manifolds on the right. And it separates two regions that we call R1 and R2. And this skinny thing that keeps going all the way around, that's a lobe, which if I play the movie and follow it forward, you'll see it is slowly marching inward. It went from R2 to R1. This wasn't exactly for the, and you see how it gets stretched and folded. This wasn't for the Duffing double-welled oscillator. This actually came from a celestial mechanics example, but the same principle holds. And we were able to compute a lobe. If I show, this is the same movie, I just sort of keep all the lobes so you could see them. And it maintains area. This is a canonical plane, so the area stays the same. So of course, as it gets long in one direction, right? It's getting, why is it getting long in one direction? It's because it's getting stretched by the unstable manifold of a periodic orbit. So it's getting elongated, but must maintain the same area. And you could even calculate that using Green's theorem of the boundary and see that it does, to machine precision, maintain area.
Out of curiosity, what do R1 and R2 correspond to in terms of realms?
They are regions inside a resonance with Jupiter, so related to asteroids moving around Jupiter.
Oh.
R1 is it's a mean motion resonance, and R2 is just outside of that.
Oh, okay.
These are things getting brought into a mean motion resonance with Jupiter. Whoops. All right. So there's more to this. These lobes and how they move around are sort of a big, at a large scale, they're what leads to chaos. And a mathematician named Smale had the insight that you could look at what's happening in a certain part of the Poincaré map and reduce that to some essential map that he called the horseshoe map. And it has to do with being very close to, if you look really close to the unstable fixed point of the Poincaré map, and you've got this whole tangle going on. If you just look at a region around here, you'll see something that looks a lot like a tangle. So I have a colleague, we were grad students together, and he drew some nice pictures that are fun to show because so now he's actually rotated what I was trying to draw the other way, and he's showing two lobes and following them as they go all the way around. So here's the red lobe is starting inside. If you want, we can call this region R1 and outside is region R2. So red is definitely inside, a lobe inside R1. Blue is a lobe inside R2. And as we march forward in time, so let's say this is at time, and I'm thinking discrete time, t equals 0. Maybe I should just say that's n equals 0. These are now, it's discrete time under the Poincaré map. Here's after one iterate of the map, the lobes have moved a little bit. Here's at n equals 2, they've moved a little bit more. N equals 3, kind of at the outer edge, n equals 4. All right, they've come back down to the other side, kind of the stable manifold side, n equals 5, and here's n equals 6. And you'll notice the blue lobe that in the upper left at the beginning was outside region R1 is now inside region R1. And if everything outside R1 we call R2, well, the red, which was inside R1, is now inside R2. If we look in more details, what's happening in this region, let me color it in yellow, that I'm highlighting, that's near where all these tangles are happening. You know, what's going on there? This figure gives a nice illustration. He actually made these with colored pencils. He just drew it and made it with colored pencils because it was a lot easier than trying to draw it on a computer. So this is showing around that lobe. Let me see, let me go up here. I guess he originally colored it red. Now he's coloring it blue and showing the two sides of it. So we're kind of looking at right over here. We've got this blue central region surrounded by green and red. And we'll follow that around. So here's what it's going to look like originally. And then after one iterate, two iterates, three iterates, and then he just kind of ran it around. So 4 iterates over here, 5, 6. What happened? Well, we have the green and red rectangles have now reoriented. And so instead of kind of being along that way, looking over here, now they're along this way, and the blue thing got kicked out. So the red and green rectangles stay in R1, region R1. Blue gets removed. So in this case, we could look at just a piece of phase space around here and define a map that, because it took 6 iterations of the Poincaré map to go all the way around, we'll define a map which is f is p to the 6th, and just look at this little domain, we'll call it D, and look at that map, how D goes to itself. And this is called the horseshoe map, because if you look in detail at what's happening around here, it looks like a square has been shaped into a horseshoe. So let me just, let me show that. If I'm gonna draw a square, that square, but make it a little bit bigger. So here's that domain D originally, and I've got a region H1, which I guess we had, green, and then H2 or H0, which is red, and the inside, which is blue. Topologically, what we did is we took this square, or what the dynamics of this forced system, this what's called a homoclinic tangle, what it ended up doing was taking this square, stretching it in one direction. So here's my little schematic of stretching it. Here's H1, here's H0, and then folding it back. So this is the stretch step. And then we fold H0. So we just we took this rectangle and folded it back. 0, H1. What color did I give this? Green, and then red, and then blue. We threw the blue out. So throw the blue, actually just the middle segment, middle rectangle away. So we take this and intersect it with the original square. And then we have, because we stretch this into a horseshoe shape, so this is the stretching and folding into a horseshoe. This region, which was H0, the H0 rectangle, it's now instead of being a horizontal rectangle, H, horizontal, it's now a vertical rectangle. So this vertical rectangle, we'll call it V0, is F of H0. And same thing over here. This vertical rectangle is a mapping of H1. And the middle part, it's just gone. It's just kicked out. So going directly from here to here, we call this the horseshoe map. And so this was by Smale. So Smale's insight was that the dynamics near the unstable periodic orbit or unstable fixed point of the Poincaré map is topologically equivalent to this sort of contrived map of taking a little square phase space and stretching it and folding it and mapping it back onto itself. And so all we have to do is analyze this simple map. And even, it looks simple, but it's got some interesting implications. There's a nice set of videos made by Robert Grist on He's a professor at Illinois, and he's done some fantastic videos. I wanted to show you one of them here. Here's his video showing the definition of the horseshoe map. So take the square face space, stretch it and fold it back, and then only keep those two rectangles. So he's colored them blue and orange, and then he threw out the purple. So that's how you define one iterate of the horseshoe map. So that's one iterate. It starts looking interesting when you do more than one iterate. So here's taking those rectangles, and now you just keep applying the map again and again. So you take phase space and you keep stretching it and folding it and throwing things out. You could do literally the same thing with a bunch of clay. If you colored the clay in these colors and it was able to stretch without breaking, you would get all of this. So you could do both forward and backward iterates of the horseshoe map. And it's nice to see the video, but I should probably explain more in some step-by-step way so you get an idea. So here, what we're supposed to see from this forward, this is the forward iteration of the map that I'm showing here. The key thing is that horizontal rectangles map to vertical rectangles. And this labeling of H0 and H1 will become important. So now what if we do a second iterate of the map? Second iterate of the map means that, okay, now we've already got these rectangles, these vertical rectangles, V0 and V1. And then we stretch, try to stretch, and then fold back and intersect. And we can, I think we can see what's going on. This is V0, this is V1. What will happen? Wow, we've got a whole bunch of little skinny rectangles to deal with here. Whoa, okay. Ooh, all right, V0, V1, V1, V0. That's hard to see, I'm sure. We'll actually label these according to the current side that it's on and then the former side that it's on. So I'll label each of these. I'll label this V0, 0, because it's currently on the left side. So think of 0 means left and 1 means right. So V0, 0, Vij, I is the current side. J is the former side. What is this? V current side is 0. So this is V0, 1. This is, the current side is 1, and it was formerly 1. That's why it's called V1. And then this is V1, 0. We could keep doing this. So this is just this is doing, oops. So this is just 2 iterates of the map. We could do n iterates of the map. And hopefully you're seeing what's happening. At each step we have, so if we have n iterates, we're going to have 2 to the n vertical rectangles. So it's going to grow pretty rapidly. But we have a way to systematically write the address. So I would have, after n of a few, they don't intersect, so I can't really draw that. We're going to have a bunch of parallel lines, and maybe they'll form some weird pattern. And for each of the lines, I could label these lines, or very, very skinny rectangles. by V, I, J, K, L, etc. And so this is going to be a sequence of zeros and ones that label the past whereabouts of the initial conditions or the parts of phase space that are on that line. Labels the past whereabouts. Points on that line. They all share the same past whereabouts. And we don't mean just any whereabouts. We mean whereabouts with respect to, was it on the left, which was a 0, or right? And after a while, right, so you've got these things that could all be given some address of zeros and ones, and maybe different sequences could be arbitrarily close to each other. If we take n goes to infinity, then this is the collection. We'll have a collection of an infinite number of lines. And this will be a collection of all infinite labeled lines that stay within the domain D, right? Everything else is getting thrown out. And for reasons that we'll talk about later, we're going to call that lambda minus. So this is the collection of things that have it's a semi-infinite sequence. It's a sequence that goes forward indefinitely, a bunch of ones and zeros. But it does have a beginning. The beginning is like the initial condition. Now, the next step is to look at what happens if you go backward under the horseshoe map. Backward, so going backward. This would correspond to going backward in time. If you go backward under the horseshoe map, then our initial, the rectangles that we labeled, H0 and H1, you actually stretch it. So we're trying to construct F inverse. The inverse of our map is going backward. So you take this and squish it and stretch it horizontally. So this is H1, and this is H0. And then you stretch and fold making the horseshoe go the other way and then intersect with the original square. And you do that many, many times. So what are we doing? We're going to construct something we're going to call lambda plus. This is just the domain D intersected with everything that remains after doing an inverse, intersected with everything that remains after doing two inverses, etc. So this is the set of all points that remain in the square D under all future iterates of F. So future is where we get that plus. That's why we label it plus. And the reason we labeled this other thing lambda minus, because it's D intersected with forward iterate of the horseshoe map, D plus two iterates, so on. This is the set of all points that remain in D under all backward iterates of F. under all backward iterates of f, meaning under all iterates of f minus. And so we already saw what this was. This was a collection of a bunch of vertical lines. Lambda plus is actually a collection of a bunch of horizontal lines. So what if I wanted to construct a collection of all points that remain in D under all past and future iterates? Then that would be the intersection of these two things. So I'll just call that lambda. Lambda is lambda plus intersected with lambda minus. Set of all points, remaining in D for all past and future iterates. And we can kind of geometrically see what this is going to lead to. If you've got lambda plus, which is a bunch of vertical parallel lines intersected with a bunch of horizontal lines, what will you get? Well, what you're going to get is a bunch of individual points where these two infinite sets of lines intersect. So it's going to be an infinite cloud of points. Or I guess I should say it's a cloud of infinite points. And it's technically called a Cantor set. So a Cantor set is a set where each point, it's a closed set that's consisting entirely of boundary points. And here's just a little cool aside about, here's how you construct a Cantor set. You start with the unit interval. And then let's just remove the middle third. If you remove the middle third, then you'll get two intervals that look like that. Now remove the middle third of each of the remaining intervals. And then just keep on going. After a while, right, you'll get to, k goes to infinity. And there's going to be just a bunch of points left, an infinite number of points. And it's a closed set that's entirely boundary points. So Cantor sets are kind of weird. See, I think I have a video that shows the construction of this thing that we call lambda. This is the, it's actually called, it's the invariant set. Because it's the set that remains in the square for all past and future time. So it's the invariant set of F, which, remember what F was? F was the map that makes the horseshoe map, and that's just, it comes from the Poincaré map for the time periodic system. Let me see if I can get that. This is also from Robert Christ. So it's like we're intersecting the horizontal rectangles and vertical rectangles. So the number of, I think to keep your eye on are the white squares. Every time the number of white squares increases dramatically. And so these are the number of, these are the points that remain in the square, the initial square, as time goes on. And it's, you keep on doing this procedure, what we're going to end up with is just a cloud of points. and it just kind of keeps on going, and it's cool. And then you might be wondering, all right, big deal. Okay, here's a big deal. For each of these points, to each of these points, we can give an address, an infinite address. Each point in this invariant set has a unique address. So like a point might have the address 0, 1, 1, 0. Then we'll just use a point here, 1, 1, 0, 1. And what this labels is where it currently is just to the right of the decimal. So this is the current location. And then the next is the next location right before the decimal. This is the previous location. Basically, we have a list of the whereabouts. So this specifies the phase space point's whereabouts in terms of which horizontal rectangle it was. As this point, think of this as an initial condition as it moves forward and backward in time. But then it's also forward and backward under this horseshoe map.
So this address format is different. So this address format is different from the other format, and then and that all of these points always stay in the region, whereas the others don't. Or is it
this is what's left. It's the same scheme for labeling. It's just these are the ones that are infinite. Right. If anything was finite, then after a while it got thrown out. Maybe it survived 100 iterates and then got thrown out.
Okay.
So the address labels the phase space points whereabouts. With respect to which horizontal rectangle. H0 or H1 as it moves forward and backward in time. So that's kind of cool. We went from dynamical systems, right? You specify some initial condition, which could be any point, right? We specify two real numbers and that gives an X and a Y. But now we've got this kind of discrete binary description of the dynamics that kind of naturally arose out of this intersecting of stable and unstable manifolds. And this is where if you want to know more about it, you will have to read ahead or read on your own. But there's a topological equivalence between this horseshoe map F and something called the shift map. On the space of sequences. And the shift map is basically just moving the decimal. So if I have this same address written above, moving the decimal over to here basically means I've gone forward in time. So the shift map takes in a sequence, let's say S, N, and I'll label the shift map as sigma. It says, okay, where are we at time N+1? And you can have two nearby phase space points that might be very similar in their sequence, but then after a while they will diverge. And so this is related to the idea of chaos. If you have two initial conditions which are very similar, then they may have similar behavior for a while, but then of course they will diverge. So you can even, just like we can define closeness of 2 points in Euclidean space, we can define a notion of closeness for sequences. So if I have a sequence, I'll write it as S. A sequence is a sequence of numbers, so I'll write this as S minus K, S minus 2, S minus 1, S0, S1, S2. Here, right, I is either 0 or 1. We're just writing down, it's an infinite sequence. Let's say I have another sequence, I'll call it S bar. So this is S bar minus K, S bar minus 2, S bar 1, S bar 2, S bar K. These two sequences, we would say the two sequences are close if they agree exactly on over a central block. So if, let's say, from negative K to K, if it's the exact same sequence over that block, and it differs outside of it, but if it agrees over that central block, then we would say those two sequences are close. And as K gets bigger, that means these two sequences are closer and closer. So I'm just trying to write down a metric, a measure, a distance function in the space of sequences. And so this makes sense. It should make sense intuitively because the two sequences agreeing on a central block in terms of dynamics means they have the same past and future whereabouts, at least over a certain finite amount of time. So that would mean common behavior over a finite time. So let's say from negative kth to kth symbol. And we can define a metric to capture this. Metric just means a distance function between two sequences. So here's D. The distance between a sequence S and the sequence S bar, we can write it this way. We kind of march through the sequence, and this is infinite. So this index I goes from negative infinity to infinity. Right, if the ith values agree, then absolute value of Si minus Si bar will be 0. We don't want this thing to blow up, so we'll add something here. Plus, we want to put more weight on things closer to the central block, so we can write this, put a scaling of 1/2 raised to the ith power, which means if things agree far away from 0, far away from the central block, it doesn't matter as much as if they agree close to the central block. So this is it. This satisfies, if you've taken metric space theory, this satisfies the criteria for a metric. And so how this is interpreted in terms of dynamics is that two nearby sequences match for a while, but then they could be totally incoherent outside of it. So things can have close initial conditions, but then they will disagree. then they can totally disagree. And maybe the more startling thing that I should say is that any sequence that you can think of, any combination of zeros and ones, there is a point, there's an initial condition that corresponds to that. So for any sequence of zeros and ones that you can think of, and it could be infinite, there's an initial condition corresponding to that. And the dynamics matches that exactly. So there's two main categories. There would be periodic sequences. So let's say 0, 1, 0, 1, 0, 1, but just forever and ever. 0, 1, 0, 1. Going in backward time and forward time. That corresponds to a periodic orbit. So a periodic orbit exists that matches this sequence. And so that's a consequence of just finding a region that is topologically conjugate to the horseshoe dynamics, which all we needed for that to happen is that the stable and unstable manifolds, instead of exactly coinciding, they split and intersect in these infinite number of ways. And then there'll be a region. And sometimes people have calculated this. Often they just sort of don't, but you can calculate it. So there could be, there's periodic sequences of all different periods. This is something that has a period of 2, right? It comes back after a while, but you could have any periodic sequence. Maybe I've got 0, 1, 1, 1, 0, 1, 1, and it keeps doing that. 0, 1, 1, 1, 0, 1, 1, forever and ever, keeps repeating that. You can have periodic sequences, and then you could have sequences that never repeat, just like the digits of pi, never repeat. If you turn the digits of pi into a binary version, well, that's a sequence. And there is going to be an initial condition whose dynamics matches that. And since it's not periodic, it is chaotic. So, I mean, it's hard to, what's a chaotic sequence? I guess it'd be like an infinite set of letters that don't seem to repeat and don't make any sense. But we can think of it dynamically. Those are chaotic trajectories. So they never repeat the sequence. So just by identifying there's a part of your phase space that where horseshoe dynamics holds, you get all of this stuff for free. People have proven it already. So there are periodic orbits of all different periods. Any sequence you could think of, there's initial conditions that match that. And there are chaotic trajectories. So the reason this has been studied, it's a lot of it is due to Smale's work in the 1960s, that this is a case where you can prove chaos. I mean, we could be pretty confident that, wow, that looks chaotic for all kinds of things. This is a situation where chaos can be proven. So if you want to know more, I'll provide references for that. But getting back to all that was necessary was that, you know, how did we get here? And this is sometimes called, all this stuff up here, because it has to do with symbols, it's called symbolic dynamics. And to get there, we needed to have a homoclinic tangle. So homoclinic tangle implies chaos and symbolic dynamics. So this was appreciated a few decades ago. So some perturbation methods were derived to see if you could analytically demonstrate if there's going to be a homoclinic tangle. Basically, when will the stable and unstable manifolds, instead of coinciding, split? So Melnikov came up with a method. This is called the Melnikov, and I think it's from 1963. So the Melnikov method can analytically prove the existence of a homoclinic tangle. And if you could prove that there's a homoclinic tangle, then you could prove that there's chaos in symbolic dynamics. So people have actually used the Melnikov method for some systems. It's actually pretty hard to do outside of 1 degree of freedom. But there's a method, and Melnikov was mostly concerned with Hamiltonian systems with some perturbation that wasn't necessarily Hamiltonian. So I'm just going to give you, because there's only like 5 minutes left or so, a thumbnail sketch of what this Melnikov method is. It deals with 1 degree of freedom Hamiltonian systems. Well, I'll discuss it with 1 degree of freedom Hamiltonian systems, but I think people have done n degree of freedom generalizations. So a Hamiltonian system with a general perturbation, meaning the perturbation isn't necessarily Hamiltonian. It could be, meaning it could be dissipative. So if we have a 1 degree of freedom Hamiltonian system, that means our phase space is R2. And we've got some Hamiltonian function, xy. Then Hamilton's equations, or the equations of motion for this system, are x dot equals partial h partial y plus epsilon, where epsilon is small, times a general function here, g1, a function of x, y, t, and possibly epsilon. So epsilon is a small perturbation parameter. Y dot is negative partial h partial x plus epsilon g2 x, y, t, epsilon. And we'll assume that that G1 and G2 are periodic in time with the frequency omega. So that means instead of G1 and G2 being a function of time, we could define a phase, theta equals omega t, and then G1 is a function of x, y, theta, and epsilon G2. Woo, I lost it here. G2 x, y, theta, and epsilon, G1, x, y, theta, epsilon. Then we can write this in, we want to write this ODE in vector form. So we'll use Q equals X, Y, column vector. And then this ODE looks like Q dot equals J times gradient of H, which is a function of Q, plus epsilon G, which is a function of Q, theta, epsilon, where J, this is just the canonical symplectic matrix in 1 degree of freedom. Now for this method to work, the unperturbed case, which means for epsilon equal to 0, must have a saddle equilibrium point with a homoclinic orbit. So that means, like we've drawn a bunch of times now, there's an equilibrium point and it's got stable and unstable direction, and they exactly coincide. It's actually not hard to make something like that. And we'll call this the trajectory that's along, that's the unperturbed homoclinic orbit. We'll just call that Q0T. And then when you perturb, so that means make epsilon not equal to 0. Now we still remember the unperturbed homoclinic orbit, and so we're kind of writing it in shadow here, and that's P0. But we also have that because we've turned on the perturbation, maybe that point has shifted, and now we're looking at the Poincaré map, and the stable and unstable manifolds have moved. So I'm going to draw, this is the, what's this, the unstable direction? Yeah. So here's the unstable direction, and then here's the stable direction. We pick a point Q. Usually it's like on some kind of point of symmetry, a point Q, and then we're defining, we're looking at the distance between the points. Whoa, I don't want that. We're looking at the distance between the stable and unstable manifold of for the perturbed case. So this is the stable manifold, and then this orange thing is the unstable manifold, and we are looking at a distance, because I should draw it that way. D P epsilon is the distance between the perturbed, stable, and unstable manifold. And what you can do is calculate that distance and see if that distance ever goes to 0 along trajectories. Or so in this case, if these two do intersect, then at some point that distance goes to 0, which means they're intersecting each other. You draw the zeros. If you get any zeros, that means they cross. They're either exactly coincide, like in this case, it's D, the distance is 0 everywhere. When you turn on the perturbation, the distance will be a function of location along the trajectory. So we could call that location along the trajectory T0. And so you would get some kind of thing that looks like that. So if you have zeros, if you have 1 0, then you have to have an infinite number of them. So then you look for zeros of D. You only need 1. Because once you found 1, there must be an infinite number. So the distance going to 0 means that the stable and unstable manifolds of that fixed point intersect infinitely many times. So you often can find this analytically. So this can be done analytically for some problems. So for example, Duffing, the Duffing system with forcing, epsilon, and damping. If you remember, that was delta. And then you can even plot, and this will be like the final thing I show. Yeah. Here's a surface that you can plot where if you're below the surface, so and this is a surface written in delta gamma. I don't know what gamma is. I think gamma is what I call epsilon. And then omega is the forcing. So if the parameters are below this surface, then the distance goes to 0. Distance between stable and unstable. Goes to 0, which implies chaos. So for some systems, you can prove chaos. And I've seen this done for a few things in the AOE department. So it's kind of fun to be able to do that. Wiggins' book goes through that in a chapter that I'll provide in the references. But I'll end